Let us calculate the absolute pressure as well as the gauge pressure that this lizard is experiencing. This is another silly example with a manatee and a lizard. What you see here is one, the picture I drew is very much not to scale. It's just to be able to show us what's going on. And two, I made it so that all the units are really, really annoying. We have a mixture of a bunch of different things. So the very first thing that we want to do is, well, we'll convert it all to SI units before we even do any analysis. So we're given that the manatee and the lizard have a mass. We're given the specific gravity of the lake where the manatee is floating with this boat. And we know the density of the water as well as the atmospheric pressure. Okay, so let's convert to SI units. It is given that 1 atm is 101,325 Pascal. That's the SI unit for pressure. So let me replace this 1 atm unit with 101,325, and here it is. The mass of the lizard and the mass of the manatee are not in the same unit. The SI unit for mass is kilograms. So let's convert grams of lizard to kilograms of lizard. So we do thusly. Now they're both in SI. We are given specific gravity. Specific gravity is, of course, unitless, and I need to know the density of the lake. What do I do? So let's look at the definition of specific gravity again, it being the ratio of the density of the substance to the density of water. We are given the density of water, and the density of water is thankfully given in SI units. Kilograms and meters cubed are both in SI. So what I'll do, knowing the SG is 1.05 unitless, and knowing the rho of water is 1,000, I can put them in. Then I can solve for rho of lake. Rho of lake would be 1050 kilograms per meters cubed. So I can replace that now with 1050 kilograms per meters cubed. Other annoying bits, the depth of the lizard that diving beneath the manatee is in feet. That's not SI. So let's convert that. Knowing that the ratio between meters and feet is 0.3048, we can convert it to 0.91 meters. Additionally, the area about, that the lizard is experiencing all the pressure from is 1 inch squared. And again, I'm reminding you, this is not the scale. An inch squared is significantly smaller than 2 meters squared. So I'm just doing this for the purpose of illustration. Let's convert the inch squared to meters squared being the SI unit for area. I don't know the uh, conversion factor from inch squared to meter squared, and neither should you ever bother to memorize that. But knowing an inch to a meter, that is important, and then we can square it. So what I do is I always use this trick rather than trying to find the actual conversion from meter squared to inch squared. I just use this and I squared the entire thing. So 0.0254 gets squared, m gets squared, 1 gets squared, and inch gets squared. And dimensionally, the inches squared go away and I get meters squared. Much easier to do it this way. Then I get the area then of the lizard's head being that quite small, you could see. All right. Now, let me re-summarize that, and so we can have some workspace to use. Everything here is an SI, so imagine had this been the beginning of the question, you could have started right here, but I had us go through an exercise of unit conversion. Why not? This happens quite often. All right, to actually do the analysis here, the lizard is experiencing 3 pressures above its head. The lake is exerting a pressure, right? The water, the actual water above the lizard's head. The manatee is exerting pressure, and the air above the manatee is exerting pressure. So there are 3 things above the lizard that are pressing down on it. Okay, so let's look at that. The lake is a fluid, so I'm going to use rho gh. We'll get to that in a second. Rho gh being a much more convenient way to calculate the pressure of a fluid. The pressure from the manatee being a solid, I'm going to use F over A rather than rho GH. That's what you would want to use for solids. Okay, the force that the manatee is exerting is mass times G. So I'm just going to use mg, and I'm going to ignore the mass of the boat. presumably the manatee is significantly more massive than the boat or something. I'm just ignoring the mass of the boat. And I'm going to divide by the area of the boat. Lastly, it's the air pressure. Well, I could use rho GH to calculate that. As a reminder, air pressure is just given an average value, and it was always already given in the question. It's just 101,325. So why recalculate that? Why reinvent the wheel? Okay, so number 3 is given. Then we're going to calculate 1, and we're going to calculate 2, and we're going to add them all up. That's going to be the pressure that the lizard will experience. And that's going to be the absolute pressure that the lizard is experiencing. Okay, so let's do that. For number 1, rho GH, I have rho, I have H. H is the depth the lizard is diving. Rho is the density of the lake. I'm going to substitute these values in, G being the gravitational constant. Everything I put in is an SI because I made sure everything was an SI. And why do I do that? So that my answers are going to be an SI. So I don't have to do any unit analysis when I'm actually doing the engineering analysis. So in this particular case, I'm just going to cancel it all out, and I'm going to be trusting that the answer is going to be in SI Pascal. And it is. And you could do the unit analysis to double check that. The meter squared canceling, and you will get Newton per meter squared. Okay, so that's the pressure of the lake above the lizard's head. Now I gotta calculate the pressure from the manatee on the lizard's head. So to do that, I have the area of the boat is given to me as 2 meters squared. I have the mass of the manatee as 500 kilograms, and I know the gravitational constant again. Yet again, I don't have to think about unit analysis because I already took care of it. So I substitute all the values in, and I get the pressure from the manatee. I can replace the red writing here with the pressure from the manatee, and now I have all 3 pressures. The pressure from the lake, the pressure from the manatee, the pressure from the air. I can add them all up, and when I add them all up, I will get the pressure that the lizard is experiencing. Here it is. So the pressure that the lizard will experience is 113,150 Pascal. That's the absolute pressure, meaning that this is the true value of pressure that the lizard is experiencing. There you go. I was also asked in the question, you can see I calculate the absolute pressure and the gauge pressure. It's going to be a quick calculation to get the gauge pressure. Gauge pressure is defined as the pressure that you actually have, the one that you measure, the one that you actually have, and you subtract the atmospheric pressure, the pressure due to air. Well, that's basically just adding 1 and 2, or if you want, add 1, 2, and 3 and subtract 3. That's really what we're doing. So you take 113,150 and you subtract 101,325, and you get that the gauge pressure that the lizard is experiencing is 11,825. The significance of this gauge pressure, again, is if it were 0, that would mean that the pressure, the absolute pressure that the lizard is experiencing is equal to the pressure of the atmosphere. If it were negative, that means the lizard was experiencing some sort of a suction upward. And if it was positive, that means it's being pressed downward. There's more pressure from above. It's higher than the atmospheric pressure, which we know is true.